The era of living drugs has arrived, but what we have seen so far, specifically the first wave of chimeric antigen receptor, or CAR T-cell therapy, was just the opening salvo. While CAR T-cells have performed absolute miracles for blood cancers, dragging patients back from the brink of death, they remain incredibly expensive, bespoke, and fraught with dangerous toxicities like cytokine storms. But nature has a backup system. Enter the natural killer cell, or NK cell. If T cells are the infantry that need specific orders to attack, NK cells are the immune system's elite SWAT team, born ready to kill. Today on G Fun Facts Online, we are doing a deep dive into how scientists are not just harnessing these cells, but fundamentally upgrading them. We are witnessing the rise of supernatural killer cells, immune warriors armored against tumor defenses, equipped with synthetic guidance systems, and manufactured off the shelf for thousands of patients at a time. To understand why these super NK cells are such a revolutionary leap forward, we first have to appreciate the standard model, the biology of the unengineered natural killer cell. Discovered in the 1970s, they were named for their ability to kill tumor cells without prior sensitization. This is a sharp contrast to T cells, which need to be presented with an antigen, essentially taught what the bad guy looks like, before they can act. NK cells work on a fascinating system called the missing self mechanism. Every healthy cell in your body presents a molecular passport called MHC class I. This molecule tells the immune system, I am part of this body, do not attack me. Viruses and cancers are clever, and they often downregulate or hide this MHC class I passport to become invisible to T cells. However, NK cells are wired to detect exactly this absence. When an NK cell encounters a cell lacking that safety passport, its inhibitory receptors are not engaged, and the kill signal proceeds immediately. This makes NK cells the perfect backup system for tumors that have learned to evade T cells. But it is not just about what is missing, it is also about what is there. Cancer cells are, by definition, stressed cells. Their rapid division and genomic instability cause them to express stress ligands on their surface, such as MICA and MICB. NK cells possess activating receptors, most notably one called NKG2D, which bind to these stress ligands. Imagine a criminal who has thrown away their ID, representing the missing self, but is also acting erratically and aggressively, representing the induced self. The NK cell spots both cues and eliminates the threat. Furthermore, NK cells are the actual effectors behind many successful antibody drugs you might have heard of, like rituximab or Herceptin. Through a mechanism called antibody-dependent cellular cytotoxicity, or ADCC, the NK cell's CD16 receptor binds to the tail of an antibody that has attached itself to a tumor cell. This triggers the release of perforin and granzymes, which are essentially molecular grenades that punch holes in the cancer cell and induce apoptosis. Now, knowing how powerful these cells are naturally, we have to look at why we need them to replace or augment CAR T therapy. CAR T therapy was the Model T of cellular engineering. It was groundbreaking, but it has limitations that prevent it from becoming a universal cure. The biggest issue is the graft versus host disease problem. T cells are extremely discriminating. If you inject T cells from a donor into a patient, the donor T cells will recognize the patient's healthy body as foreign and attack it. This is why current CAR T therapies are autologous, meaning we must harvest the patient's own blood, engineer it, and send it back. This process is slow, taking 3 to 4 weeks. It is incredibly expensive, often costing over $350,000, and it frequently fails if the patient's T cells are already exhausted from chemotherapy. This is where the NK advantage changes the game. NK cells do not cause graft versus host disease. You can take NK cells from a healthy donor, engineer them, and give them to a mismatched patient safely. This opens the door to true off-the-shelf therapy. Additionally, There is the safety profile regarding cytokine release syndrome, or CRS. CAR T cells proliferate explosively and release massive amounts of IL-6 and TNF-alpha, causing systemic inflammation that can be fatal. They also cause neurotoxicity. In clinical trials, however, NK cells produce a completely different cytokine profile, mostly IFN-gamma and GM-CSF. Severe CRS and neurotoxicity are virtually absent in CAR-NK patients, meaning these treatments could potentially be administered in outpatient settings rather than requiring a stay in the intensive care unit. But scientists are not satisfied with natural NK cells. They are enhancing them to become super NK cells using CAR-NK technology. Simply putting a T-cell CAR into an NK cell is suboptimal, because T-cell CARs use signaling domains tailored for T-cell biology, like CD28. The next generation of CAR-NK cells uses signaling domains native to NK cells, such as DAP10, DAP12, or 2B4. These domains trigger faster, more potent cytotoxicity because they align with the NK cell's internal wiring. Another major engineering feat is the armored CAR. The Achilles heel of NK cells is their short lifespan. In the body, they typically survive for only a few weeks. To turn them into durable cancer fighters, engineers are armoring them with the gene for interleukin-15. By engineering the NK cell to secrete its own IL-15, the cell stimulates its own growth and survival. This autocrine loop allows super NK cells to persist for months rather than days, patrolling the body for relapse. We are even seeing the integration of logic gating, essentially turning cells into smart bombs. Companies like Senti Biosciences are engineering logic circuits into NK cells. For example, an OR gate tells the cell to kill if it sees antigen A or antigen B, which prevents tumor escape if the cancer stops expressing one target. Even more impressive is the NOT gate. This logic circuit tells the cell to kill if it sees antigen A, but not if it sees antigen B. This is crucial for safety. For instance, in acute myeloid leukemia, we want to target CD33, which is on leukemia cells, but also on healthy stem cells. By adding a NOT gate for a marker found only on healthy stem cells, the NK cell spares the patient's bone marrow while eradicating the cancer. Beyond adding genes, we are also using CRISPR to delete the genes that hold NK cells back. One major target is the CISH gene. CISH acts as an internal brake on cytokine signaling. When CISH is deleted via CRISPR, NK cells become hypersensitive to IL-15. They grow faster, kill more aggressively, and exhibit superior metabolic fitness. These CISH knockout NK cells are effectively supercharged batteries that do not run out of energy. We can also remove the brakes imposed by the tumor itself. Tumors often express HLA-E, or poliovirus receptor, to tickle inhibitory receptors like NKG2A or TIGIT on NK cells, effectively telling them to shut down. By deleting the genes for these receptors, engineers create NK cells that are deaf to these inhibitory signals, allowing them to plow through the tumor's stop signs. In solid tumors, the microenvironment is flooded with TGF-beta, a potent immunosuppressant that paralyzes NK cells. To fix this, engineers introduce a dominant negative TGF-beta receptor. This is a dummy receptor that soaks up the TGF-beta but cuts the wire to the internal signaling pathway. The NK cell sees the suppression but is unaffected by it, remaining active even in the hostile center of a tumor. Not all engineering happens inside the cell, however. Some strategies use synthetic molecules called engagers. BiKEs, or bispecific killer engagers, are small molecules that link CD16 on the NK cell to a tumor antigen, physically dragging the NK cell onto the tumor. Tri-keys or trispecific killer engagers take this a step further by adding a third component, usually IL-15, into the bridge. A tri-key not only handcuffs the NK cell to the cancer, but also force-feeds it a growth signal right at the site of action, driving localized expansion of NK cells exactly where they are needed. Perhaps the most disruptive aspect of NK therapy is the manufacturing revolution. The goal is to move from a service model to a product model. We are looking at different sources for these cells. Peripheral blood from adult donors produces mature cytotoxic cells, but they are hard to expand to massive numbers and suffer from donor variability. Umbilical cord blood is another source. It is readily available, and the cells are naive and less immunogenic. The famous MD Anderson CD19 trial used this source with great success. But the holy grail is induced pluripotent stem cells, or iPSCs. With iPSCs, you can engineer a single stem cell with complex edits, like the CAR, the IL-15 armor, and the CRISPR knockouts. Select the perfect clone, and then expand it into a master cell bank. One bank can yield hundreds of thousands of identical doses. This is combined with new bioreactor technology and cryopreservation formulations that allow us to freeze bags of CAR-NK cells that retain over 90% viability upon thawing. This solves the logistics problem, allowing hospitals to stock cancer treatments in freezers like standard drugs. In terms of clinical frontiers, we have seen major successes. In a landmark study at MD Anderson Cancer Center, researchers treated patients with relapsed B-cell malignancies using cord blood CAR-NK cells targeting CD19. The result was a 73% response rate, with 7 of 11 patients achieving complete remission, all with 0 cases of severe CRS, neurotoxicity, or GVHD. The challenge now remains the solid tumor wall. Solid tumors like glioblastoma or ovarian cancer have a physical fortress of stroma and a chemical moat that is acidic and hypoxic. New trials are combining CAR-NK cells with oncolytic viruses to break the stroma, or targeting antigens like mesothelin. Early data suggests that armored NK cells are showing durability in these models, especially when combined with checkpoint inhibitors. Finally, we must consider the metabolic reprogramming necessary to fuel this fight. The tumor microenvironment is a starving place where cancer cells consume all the glucose, known as the Warburg effect. Super NK cells are being engineered to switch fuel sources. By overexpressing enzymes involved in fatty acid oxidation, these cells can bypass the glucose shortage and burn lipids instead. Engineers are also focusing on mitochondrial fitness to ensure the NK cell retains the ATP needed to degranulate and kill. Commercially, the economics are staggering. While CAR-T costs hundreds of thousands per dose, an allogeneic NK batch from a master cell bank could drop the cost of goods to between $10,000 and $20,000 per dose. This democratization could make cell therapy accessible to community cancer centers, not just elite academic hospitals. We are witnessing a paradigm shift from caring for cancer to engineering its destruction. The supernatural killer cell represents the convergence of immunology, synthetic biology, and industrial manufacturing. They are safer than T cells, cheaper than T cells, and with the latest genetic armor, they are becoming just as deadly. From living drugs to smart living drugs, the super NK cell is the dawn of a new immune system, built by human ingenuity to finish the fight that nature started.